Hello, welcome to our next lesson. And in this, we're going to take a look at some of the properties and procedures we use when trying to graph quadratic equations. I'm also going to link another link in your under WAMAP. And I have the link for it here. Unfortunately, as I'm giving a lecture, I can't really go to that, unfortunately. But I am going to put that in there for you to just kind of play around with. When we talk about quadratic equations, we've talked about polynomials that have a degree of 2. And specifically when we talk about quadratic functions, so we have x's and y's. And if we're talking about a quadratic function, of course, you're looking at it's set equal to y or set equal to f of x. Highest degree is 2, so ax squared plus bx plus c is what we call the standard form for a quadratic function. The values of a, b, and c really determine the location and the shape of that particular graph, but they all have a commonality in the way that the graphs look. They all make something called a parabola. And a parabola is basically a U-shaped object that goes like this. It looks like a U, but not exactly a U, but it does have a low point, or it can also have a high point, right, if it's facing downward. But this point at which it either is the lowest or the highest point, we call that the vertex. And on either side of the vertex, we have a graph that is symmetric to this line that passes through the vertex. We call this the axis of symmetry. And basically that just means that if you were to fold this graph across this line, the points would match up and touch each other. So finding the vertex for your parabola is probably one of the more important beginning points as you're learning to graph. And so we're going to take a look at that, but formula-wise, this is how we find it. We take the opposite of b over 2a. Since a, b, and c, the coefficients of the first, second, or third term, really determine how this graph is going to look, the first thing we want to find is the vertex. If you take the negative b, or I like to say the opposite of b, and then divide that by 2 times the value of a, you have the x portion of the ordered pair. So notice that it's this and then a comma, so that's the x portion. And then this says find the f of the opposite of b over 2a. In other words, plug that value into your function for x and determine what the y value is when x is equal to that. And that is how we will find the vertex when it's in standard form like this. So A specifically, and this link that I've given you here, which I will also link into WAMAP, gives you the opportunity to kind of play around with A, B, and C. And you'll see each one of these numbers as you change it does something very specific to the parabola. And you'll notice when you mess with A and change it, it changes the width or how wide or narrow the parabola is. So what we find is if we have an A value, and here I just took the absolute value of A and just said, okay, so let's take the value of A regardless of its sign. If it's between 0 and 1, what we're going to see is a much wider parabola. So if we change the A value and we had a parabola that looked like this over here, and we changed that A, and the A became a number between 0 and 1, so a fractional value, we're going to see our parabola get wider. And if it's more than 1, what we see is that parabola gets narrower. And then when A is positive, so A is greater than or actually, I'm going to go down one more than that. If A is less than 0, so it's negative, this is when we have the upside down facing parabola like we have over here. Oops. I keep on meaning to erase there, and I keep on flashing back to the other screen. All right, so that's kind of the basic ideas here. These are general principles that we can just kind of keep in mind. So we set some expectations about what our parabola is going to look like, but we're actually going to plug in actual values in there, meaning we're actually going to get points that we can plot out. But we always want to keep in mind some of these general ideas so our expectations are set in the correct direction. And hopefully our graphing kind of confirms those. So the other form that we're going to see quadratic equations sometimes written in is, we call this the vertex form, mostly because as we look at it, we can determine the vertex right away simply by looking at the value of h and k. So if something is put into vertex form from standard form, what we go through is a process of completing the square with this function up here, giving us a partial perfect square up here that we can factor, and then any numbers that are left outside we determine as part of the vertex. So looking at this, whatever the values of h and k are, I already know where the location of my vertex is, which is, of course, why we call it the vertex form. And the effects of A are the same as described above. All right. So let me just kind of give you an example here, because you do want to be careful as you're interpreting something in this form. Okay, so let's just say I have this function given to me, and we want to know the vertex of it. Well, the vertex of this would actually be, for x, at 3 and then 2. So a couple of things to unpack there. Why is it 3 and not -3? And I said, hey, I think you made a mistake there. Actually, I didn't. That is the correct x value. You'll notice that in the general equation, we have a minus in front of that h. So if x's value is 3, and I'm plugging, or I'm putting that in there, you see what we see afterwards, right? So the h value that we've substituted in there is a 3, but since I'm putting it behind a subtraction, what we see is a -3. But in actuality, the value of h, the value of the number that I substituted in there, was positive. So when you're looking on the inside with the x, we always want to take the opposite symbol that we see. And then in the general equation, we have plus k. And so if k's value is 2, and I substitute that in there, what I see is plus 2. Right? So there's different symbols depending on whether you're talking about the x, so the h, or the k. In the general formula, whenever we see a minus in front of a variable, we want to think opposite. And so the vertex here would be +3 for x and 2 for y. The 3 out front here tells me that once I start plotting things out, it's going to be much narrower. So it's going to get really steep really fast, something more along the lines of the blue here, as opposed to the red. If this was 1/3 rather than 3, so 1/3. Now we have a value that's between 0 and 1, and so we know that it would be a wider parabola. All right, so let's take a look at doing some examples here. Okay, so as we look at this example, we're going to first start off identifying what the a, b's, and c's are for this particular quadratic function, which is in standard form. The a value is -1. Notice we have that negative in front of the x squared. The b is -6, and my c is -8. So looking at these, we are told that the vertex of my parabola, which is kind of our centering point, is at the opposite of b over 2a. And then once we found that, we're going to find the f of the opposite of b over 2a. It helps to think of that negative as meaning opposite sign. So The opposite of my b is negative 6, so the opposite of 6 is, or negative 6 is positive 6, and that's over 2 times negative 1, which is 6 divided by negative 2, which is negative 3. So I know the x value of my vertex is at negative 3. And now let's find the f of negative 3, so we can find the y value of the vertex. So that is the negative of negative 3 squared minus 6 times negative 3, and then minus 8. So working this out, that is negative 3 squared is positive 9, but then there's that negative outside. So we have to keep that negative. This becomes minus negative 18. We're subtracting, so you can think of it as negative 6 times negative 3. That's positive 18. Negative 9 plus 18 is 9, and 9 minus 8 is 1. So negative 3, 1 is my vertex. So I'm going to go over here and go ahead and put at negative 3, oops. And that's positive 1, yeah. We're going to go negative 3, so back 1, 2, 3, and then up 1. We'll put a dot there for my graph. The first for this particular thing. Now, just to make some observations here, the a value is negative. So this tells me that I'm going to have a upside down parabola. So that's kind of in my expectations. Now, all I'm going to do, and this is what I want you to do as you're graphing each one of these, is to find 4 or 5 points. So, and you'll actually have to do a little less math than that, because what we see is if we're using the vertex, we have that property of symmetry that we can use to our advantage. As long as I have the correct location of the vertex, negative 3, 1, I'm going to map out a couple to the right of it, so negative 2, negative 1, and then a couple to the left of it, so negative 4, negative 5. And what we should see with symmetry is you'll notice that these 2 points, negative 2 and negative 4, are both 1 away from the vertex, and so their y outcomes should be symmetrical, should be the same y value. And the same should be true for negative 1 and negative 5. Now, once you've established the symmetry, then it's okay to not have to do the extra work. But you want to make sure that, because what happens is if your vertex is actually wrong, let's say I forgot that it's supposed to be negative 1 or it's at positive 3 instead of negative 3, that your y values become really weird, become very extreme, because you're way away from the actual vertex. So you want to establish that, hey, we're in the right ballpark here. All right, so first off, we'll start off with the f of negative 2. And the f of negative 2, that means I'm going to plug negative 2 into the function. So that's the negative of negative 2 squared minus 6 times negative 2 minus 8. So this becomes negative 4 because negative 2 squared is 4, but then this negative again attaches itself to the number. This becomes plus 12. And then going left to right, 12 minus 4 is 8, and 8 minus 8 is 0. So negative 2 gives me 0. Go ahead and put that on there. Well, I would expect negative 4 to do the same. So let's go ahead and check to see that it does. That's the negative of negative 4 squared minus 6 times negative 4 and subtracting 8. So again, that becomes negative 16 plus 24 minus 8. Okay. Well, negative 16 plus 24 is positive 8, and 8 minus 8 is 0. So again, I've established that symmetry. And so I can go ahead and plot these out as well. I'm not happy with these points, so I'm going to redo them now that I'm zoomed in here a little bit better. Okay, so those are my first few points. Let's go ahead and plug in -1. Once I've found that, the f of -5 should be the same thing. And since I've established symmetry, I'm not going to bother to plug it in again. So let's see, -6 times -1. And then -8. So this gives me -1 plus 6 minus 8. So that's 5. And then 5 minus 8 is -3. And so -1 gives me -3, which I'm going to assume is the same value I'm going to get for -5. And if you're not sure, go ahead and double check that. But -1, -3 then would be right down here. And -5, -3 would be in a similar spot right over here. All right, this is enough now for me to go ahead and graph this equation. What we want is not a V, but a smoothly moving semi-U. But it's a U that has, so it's kind of a cross between a U and a V. It's pointing downward that we expected because we had a negative here for my A value. And it's neither more wide or more narrow because the value there for A is just a 1. So it's a pretty standard looking parabola. The idea of the parabola is it's going to continue to go down and out for eternity, right? For infinity, we should say, in either direction. It doesn't ever go vertical, so it never stops moving to the left or to the right. But this becomes steeper and steeper and steeper. And that's the idea of this. And it's not a V, it's more of a smoothed out V, making it semi-U-ish, though U would kind of have a little more of just a flat bottom. Okay, let's look at one that is in the vertex form, which we have here. If I were to carry this out, let me just kind of show you this. We can put it into standard form. Simply first, just carry this out. Take x plus 1 and multiply it by itself, or x plus 1 multiplied by itself, right? Squared it, which really involves, we have this plus 6, foiling that. So that becomes x squared plus 2x plus 1 plus 6, which now in standard form would be x squared plus 2x plus 7. You see that? Okay, so these two functions, whatever form they were given in, would graph the exact same parabola, but their forms are very different as far as how they're presented. All right, and here we have x plus 1 minus 6. The vertex I would get from this is at -1, 6. Remember that when it's on the inside, we always take the opposite sign we see for the h. And here we had the plus 1 in there. And with the formula, it's x minus h. So to get plus 1, I would have to plug in a -1, because x minus -1 actually gives me x plus 1. And so that tells me that the vertex is at -1, 6. So I'm going to go ahead and graph that. That's up here like so. And there we go. And now, using the vertex as kind of my center, I'm going to find some other points. This is the key. You got to find that vertex, because what happens is if you just pick random points, which for lines, we could do that because the line doesn't grow exponentially like we see with quadratics. It doesn't grow really fast. And let me just go back to our previous thing. You'll notice, say, for example, if I had just randomly chosen 2, which doesn't even seem like a radical value, notice that it's going to be like way down here, right? Because this is getting steeper and steeper, and so it's probably even further down. And in fact, we can see f of 2 would be negative 2 squared minus 6 times 2 minus 8. So that's negative 4 minus 12 minus 8. That, my friends, is a very steep, that's negative 24. So, yeah, I'd be down a lot further. I'd be more like down here. And that's just because I randomly picked 2, but 2 is far enough away from the vertex that it gives me a really extreme value. This is why you want to use your vertex and find that first, and then use points close to that. I wouldn't go much further out than 1 unit. You might be able to get away with going 2 units to each side, but again, be careful, because like in my graph, I have limitations here. I don't want to get much higher, right? This is an upward facing parabola because the a is positive 1. I don't want to get much further away from here and get higher than 10, which is off my graph. Now, if I have a really wide graph, because I have like a fractional value out here for a, then I can go a little bit further out in either direction. But typically, I'm just going to stick with like 1 unit. So in this case, I'm going to plug in 0 and positive 1, and then negative 2, negative 3 should be the matching points. Remember, these two should be symmetrical, and then these two are both equal distance from the vertex. All right, so f of 0. 0 is nice. Let's go ahead and back here, because it cancels out stuff. It's actually a little bit easier when it's in standard form. But, all right, let's just go ahead and plug that in. So 0 plus 1 squared plus 6. Well, that's 1 squared, which is 1 plus 6, which is 7. So I see that 0 gives me 7. And my question is, does negative 2 also give me 7? Well, let's check it out. So negative 2 plus 1 squared plus 6. So that's negative 1 squared plus 6. Well, negative 1 squared is positive 1, so that's 1 plus 6, which again is also 7. So, graphing those out here, we have our first couple of points, and they are symmetric. So as I go to find f of 1, I know that f of negative 3 should be the same thing. 1 plus 1 squared plus 6. So that's 2 squared plus 6, which is 4 plus 6, which is 10. So 1 gives me 10. I can assume negative 3 will also give me 10. So 1 and 10, negative 3 and 10. There we go. Enough points there to graph my parabola, knowing that it's going to be in the shape of a parabola, so that gives us and some of the behaviors depending on the values of a, b, and c. We're going to go ahead and do one more in vertex form, and the vertex here we see is going to be at 3, negative 2. The h is on the inside with the x, and we see, it's x minus h, so h has a value of 3. Even though we see minus 3 here, the only way we would see minus 3 is if we plugged a positive 3 in for h. So, and then the k, actually, the y value, is what we see as a subtraction of 2. Remember that in our general form, we had a plus here, and the only way to get plus would have, for that to remain the same, would have to be a plus negative. So that tells me that k is a negative 2. Okay, so here's where my vertex is. We're going to go ahead and create my table here. So let's go ahead and plot that, 3, negative 2. I can also see that the value of a here is just positive 1, since there's nothing there. That means it's going to be a normal looking parabola. It won't be more narrow, won't be wider. and it's been shifted over to 3, -2. All right, so with 3, let's go ahead and plug in 2 and 1, and then 4 and 5. Notice I just went to the left a couple and to the right a couple. And we should expect these two to match up and these two to match up. So plugging in and finding the f of 2, it's nice to be able to work with some positive numbers here. 2 minus 3 squared minus 2. That's -1 squared minus 2, which is 1 minus 2, which is -1. And let's see if we get the same thing with 4. So that's 4 minus 3 squared minus 2. So that's 1 squared minus 2, which is, again, -1. So when I go to plug in 1 then, that would be 1 minus 3. 1 minus 3 squared minus 2. And that's -2 squared minus 2. So that's 4 minus 2, which is 2. And if this is 2, then we know that 5 also should give me 2. All right. And, all right, so plugging in the rest of these, we've got 3 -1, 2 -1, and then 1 +2, and 5 +2. Connecting my points. There we have it. A couple of other things I wanted to point out. I'm going to go back to when this was in standard form here. So let's go ahead and write this up here. When we were finding solutions to quadratic equations, we were setting our equations equal to 0. In other words, we were substituting 0 in for the y. And in doing so, we're basically saying y is 0, right? And where y is equal to 0 on my x-axis, this is where y is equal to 0. You'll notice that that's 1, that's -1, 2, -2. So y is equal to 0 here on the x-axis. So when we plug 0 in there, and this is just going back to what we were doing previously, if I were to factor this out, and this particular one is factorable, I know that just by looking at the graph, that gives me x squared plus 6x plus 8. And then this is factorable with a negative on the outside, but then x and x. I want two numbers that multiply to give me 4 or 8 and add up to give me 6. Well, that's easy. That's 2 and 4. And so we see the solutions for these are -2 and -4. Notice that on my graph, -2 and -4 were the x-intercepts. In other words, they were the outcomes when y was equal to 0. So the factored solutions we found using the quadratic formula and factoring are actually giving us the x values of our intercepts. And that's just another connection I want us to make there between the quadratic equations and their particular graphs.